Hi, welcome to another lecture on Calculus 2. Today we are going to talk about the cross product. So if we have two vectors, we talked about the dot product last time. Now we are going to talk about the cross product. Cross product is something that is mainly used in physics and engineering. The most famous application there is when you have the distance vector crossed with the force vector, and in that context this is referred to as torque. So when the rotational force is to be discussed, people use the concept of torque, which is a product of the force and the distance from the point of application. Let me just take you to some places on the internet to see what this topic shows up, and then we go back to the mathematical properties of this operation. So of course, this concept of torque, you see radius or distance times the force. Typically when you have a force applied on an instrument which is attached to an axis or a location, and you are applying it in a certain rotational motion, you're dealing with the concept of torque. So the issue comes up when you are tightening the wheel nuts on your wheels. So you have to put a special wrench here to tighten these wheels, and they tell you how much torque you're supposed to apply. And well, when you're buying these special wrenches, they tell you how much you can actually apply. So two issues comes up. One is how long is the arm of this wrench, and of course how much force you are going to apply, and so on. So let's go back and take a look at the applications that we have in mind. Those of you who are taking the physics classes or engineering classes, there's also angular momentum, which is in a similar context is the radius crossed with momentum itself. So a basic physics law is that the force is equal to rate of change of momentum, and the rotational version of this is that the torque is equal to rate of change of angular momentum. Okay, let's go back to mathematics and see how we are going to deal with this. In order to introduce this concept, it would be perhaps best for me to first start with the concept of determinant, because that's how we are going to actually calculate this quantity. So determinant is a mathematical concept that is applied to so-called square matrix. So we have a matrix that could be 1 by 1, 2 by 2, 3 by 3, and so on. So this is a square matrix, and it produces a single number. So for example, determinant of, if you have just a single number in number, is just that number, no complication here. If you have a 2 by 2 matrix, which is a set of 4 numbers like this, determinant is very simple, is the cross product of these two subtracted from each other. That's AD minus BC. These are shortcut formulas that I'm going to introduce you to, and then later on we are going to go ahead, just have a quick review of the definition of a determinant using a more advanced so-called recursive definition. For 3 by 3, so if I have A, B, C, D, E, F, G, H, I, to calculate determinant of the 3 by 3, we have a device to help us memorize how it happens, but it's simply for memorization, and really not much can be built upon that. Determinant is a very complicated function There isn't really a way of simplifying it. The formula for it expands with the size of uh, the matrix quite rapidly, indicating that there cannot be any shortcut. But here for 2 by 2 and 3 by 3, which is the case that you come across most often, there are some shortcuts. So here, if let me introduce you to this shortcut. Probably you have seen that in some other classes, maybe your linear algebra class or some high school algebra class. So if I want to calculate the determinant of this 3 by 3, first thing that I do, I just go ahead and duplicate it. So A, B, C, D, E, F, G, H, I. Then I consider the diagonals. Well, there are lots of diagonals here. Number 1, number 2, number 3. I take these blue diagonals, multiply them by pluses, and then I go in the opposite direction. So A, F, H, B, D, I, C, E, G, and multiply these by -1. So there will be 6 diagonals total. 3 of them multiplied by pluses, 3 of them multiplied by minuses, and we collect all of these and throw them in a single bag, if you wish to call it like that. A, E, I, and then B, F, G, and then C, D, H. Then I have minus A, F, H, minus B, D, I, and minus final one, C, E, G. If you want to economize a little bit, you can skip the very last column and notice that this is same as the last product there. So if you want to make it a little bit shorter, you can do so. So we see that here's a product that we have 6 terms. Each term is made of product of 3 numbers. These numbers that are chosen here, all of them belong to different rows and columns. No 2 of these things are on the same row or on the same column. So that is how the elements are picked up. And there is also a rule for pluses and minuses that's a bit complicated. We are going to postpone that to your linear algebra class. Now it's very important to realize this is just a device for memorizing. Really not much can be built on that, meaning if I go to the next level, that is a 4 by 4 matrix, this simple idea of drawing diagonals is not going to work anymore. In fact, there are going to be 24 terms in that expansion. And then if I go to 5 by 5 matrix, it's going to be 120 terms and so on. So you can imagine if something has 120 terms in it, simplifying it, it's not going to be a task. So how many terms do we have? 1, 2, 6, 24, 120. How does it go? So this is a famous sequence we have seen many times. This is going to be n factorial terms. These are all terms are made out of products of entries from the rows and columns. Each product has exactly 1 entry from each row and each column. Half of them come with multiplied with the plus ones, and the other half multiplied with minus ones. As I said, in reality, we just work with these two, unless you go to your linear algebra class and then you have more advanced versions of these things. Okay, now it's possible for the entries of this matrix to be vectors themselves, meaning AB can be considered as a vector, CD can be considered as a vector, and so on. So let's go ahead and start with the concept of the cross product of 2 vectors. Cross product of 2 vectors uh, can be built on the concept of determinant in the following way. Suppose I have a matrix A, which is, well, 3 components, and a matrix B, well, that is also 3 components. A cross B is defined as determinant of a matrix whose first row just made out of the standard unit vectors I, j, k. The second row is the first of these things, which is a1, a2, a3, and the last one is the second of these two vectors, b1, b2, b3. So A cross B can be defined as such a structure. Well, one way to simplify these 6 items that we have here is to collect the items that are multiplying vector I, the ones vector j and vector k. Remember, in this context, this I, j, k are not numbers, rather they are vectors. So I can summarize it in the following way. Out comes a vector. That vector is going to have components I, j, k in them. And then there's going to be so many i's, so many j's, and so many k's. The multiple of I is going to be a2, b3 minus a3, b2. The multiple of j is a3, b1 minus a1, b3, and the multiple of k is going to be a1, b2 minus a2, b1. So that is how we do the product of two vectors. Let's just go ahead and practice, make sure we understand what's involved here. Suppose my A is the vectors 1 minus 2, okay, so let's see, 1 minus 2, 1. B is the vector, say, 3, 1, minus 2. The question is, well, what is A cross B? Well, we said this is the determinant of such a matrix. On the first row, we have just I, j, k. So remember, I, j, k was the notation we were using for vectors. So if you want to write this thing as a vector, you could write it as 1i minus 2j, 1k, and so on. So I just write the first vector here, the second vector here, 3, 1, minus 2. Out comes a vector which has 3 components, I, j, and let me make more space. 2. So what is the multiple of I? So multiple of I is the product of these two numbers, minus 2 times minus 2, and minus 1 times 1. And then j, so j, 1 times 3, minus 1 is this one, times minus 2, and finally we have the last entry, which is k, and that's going to be 1 times 1, so 1 times 1 minus 2 times 3, and it simplifies to, this is 3i, and then I have 5j and 7k. So if you want to abbreviate this. 3, 5, 7 is the product. What if you wanted to apply the notation we had here for duplicating your matrix? Well, let's do it that way as well. So if I have I, J, K, 1, minus 2, 1, 3, 1, minus 2, I just copy it. I, J, K, 1, minus 2, 1, 3, 1, minus 2, and then this one, this one, this one, and so these multiplied by pluses, this multiplied by minuses, and then we threw all in the same bag. So this one is going to give me I times minus 2. So let's write it. I minus 2 minus 2, J 1 3, K 1 1, going backward, minus I 1 1, minus J 1 minus 2, and minus K minus 2 3. I put everything in parentheses so we don't make a mistake. Okay, so this is 4I minus I, so it becomes 3I. 3I plus 2I makes 5I. K minus 6K, so that's upward 7K, same thing that we got up here. So that is how to multiply it. Now if you have two vectors in 2 dimension, you can imagine them that the third component is 0. In that case you plug zeros here and then you multiply them, you get a vector that's going to be purely in the k direction. So that is a standard problem you see. So let's go ahead and list some properties. Algebraic properties of cross product. Many of these things tie in with the properties of determinants, but we are not going to open that can of worms with respect to determinant. These are all very easy to observe or prove. First of all, when you are multiplying two vectors, finding their cross product, this is the first instance where the order of multiplication is going to be important. If you switch the order, the product is going to flip, meaning it becomes negative of itself. So that is an important property. So we don't have commutativity, rather we have whatever you want to call this thing, anti-commutative or something. The sign flips. Fortunately, we still have this property of multiplication that we had. So we are using the same notation as multiplication back in elementary school, but entirely different animals intended here. So this kind of distributive property still there, and that's also easy to show. If you have a cross product and then you want to multiply it by a number, you have several choices. You can take the first vector, multiply it first and then with the second, or you can take the second vector and scale it up. It's all same. One other thing, if you want to do a cross with the 0 vector, all you get is just the 0 vector, as you suspect. An interesting property is that if you take a vector and cross it with itself, okay, I invite you to try to figure that out. That is, before I write it, you want to pause this. Just write 1 minus 2 1 and 1 minus 2 1, same set of numbers. Okay, so it's a good place for you to practice this thing and come back. So that's a 1-minute exercise. What's a cross product of a vector with itself? Okay, surprising answer, comes out of one of the properties of determinant? And the answer is 0. In fact, if you have a determinant that 2 rows of it are the same, you get 0 as a result of determinant. Or if 2 columns are the same thing. And they don't even have to be the same. If one of them, just one row, is a multiple of another row, that determinant just becomes 0, and so on. So that we have that property. We have another property which is mixing our dot products with a cross product. If I have a vector and I dot it with the cross product of 2 other vectors, now you have 6 ways of doing this thing, and they for the most part they turn out to be the same. So if I have A dotted with B cross C, that is same as B dotted with C cross A, that is same as C dotted with A cross B. Notice that these are all in the same rotation. Like if I have A, B, C, excuse me, A, B, C, back to A. So I have A, B, C, A, B, C, and then I have B, C, A, and then C, A, B. These products all turn out to be the same, and all of them are equal to determinant of a matrix whose first row is A1, A2, A3, second is B1, B2, B3, and third one is C1, C2, C3. These are all turn out to be the same. Okay, and many other properties. One of the perhaps most complicated properties to memorize and actually to show by detailed work is double cross product. If I have A cross B cross C, something that we had in the context of figuring out properties of a curve when we're talking about the radius of curvature and so on and such. This is turns out to be B times A dot C minus C times A dot B. That takes a bit of time to show, so we are feeling ambitious and want a good amount of basic algebra. Is like a lengthy algebra exercise to show that these are the same thing. But again, we just have a lot of other things to do, so we are going to leave that to you to show. So these are some of the properties of cross product. We list them under algebraic properties, just well, algebra. Now let's go ahead, make a bit sense of what does this thing really represent. So one way to understand that is geometric properties. What are we trying to achieve by this rather complicated operation? First of all, A cross B, let me write in another column, A cross B is a vector that is perpendicular to both A and B. So best way to show that is to say, okay, suppose I have a plane and I have a vector A here and I have a vector B here. So A cross B will be a vector that is perpendicular to both of these, and the result is going to be perpendicular to the plane on which they are sitting. So A cross B is going to go in that direction. So that's one standard way of finding a vector perpendicular to a plane if you have two vectors sitting in that plane. Well, those of you who are paying close attention notice that perpendicular to a plane can go in two opposite directions, red and blue. Which one of them do you want? And here is a standard so-called right hand rule. If you take your hand and rotate it from A to B, okay, so we rotate A to B, then our thumb is going to be thumb of right hand is going to be in direction of A cross B. So that is one way to remember that. Another thing about the cross product is that A cross B is equal to the length of A times the length of B times sine of the angle between the two of them. Again, this angle that we have here. So that is also something that we can show by doing a little bit of algebra, and I'm going to leave it to you to read it in the textbook itself. Now you notice that, well, if A and B are lining up, either the angle is 0 or the angle is 180 degrees, that sine is going to be 0, and as a result A cross B is going to be 0. So one way to figure out something about two vectors is that if their cross product is equal to 0, it implies A and B are in the same line. They are either parallel or anti-parallel. So however you want to phrase it, A and B are multiples of each other. In particular, the cross product of a vector with itself is 0, and of course with any multiple of itself. One of the more interesting application of this thing is that A cross B in absolute value is equal to the area of the parallelogram whose adjacent sides are A and B, with sides A and B, meaning if you go ahead make a parallelogram with this, and here's the parallelogram, the area of this parallelogram numerically is equal to the length of that the vector that we have. So that is an algebraic property of this. Now we have one more of these things with respect to A dot B cross C. A dot B cross C, this is equal to the volume of a prism built on top of A, B, and C. Meaning, if I have A, B, and C, and then I make a kind of a slanted box with this thing, something like this. A dot B cross C in absolute value. So this thing is a number, so it can be positive or negative, but the absolute value of it is equal to the volume of that prism that you see over there. So that's another property of these things that comes in handy. So we see many of these applications, and most of it comes up in the context of physics. So we said when you come to second half of dynamics and such, you're dealing with the rotational motion. You see the torque being defined as arm or radius times the vector itself. So that is an application in physics or engineering. Also, we have angular momentum. Angular momentum is also equal to radius times momentum itself, and these two are related to each other same way that the force and momentum are related to each other. Okay, this is a topic that just requires quite a bit of practice for it to settle in your mind. I left out some of the proofs for you to do. You'll see it in your textbook as well, and I hope you'll have fun with it. Okay, until next time, good luck and God bless.